is our guest today, and he has been a faculty member in the School of Mechanical and Materials Engineering at IIT Mandi since 2015. After completing his PhD from Indian Institute of Technology, Kanpur, in 2009, he worked with ANSYS Fluent India Private Limited in the development department for around 6.5 years. He is currently working in the area of radiative heat transfer, fluid mechanics, solar devices, etc., and uses computational tools for his research activity. He is extremely interested in exploring and developing open source software. His team is currently developing various features of radiative heat transfer like collimated beam radiation, non-gray radiation model, etc. in open form as an open source CFD software for the applications of solar receiver cavity, combustion, and thermal load on the rocket base plate, IR signature of hot plumes, etc. So it is our pleasure to host Professor Pradeep Kumar, who is going to talk about modeling of gaseous radiation for the application of combustion and plume radiation, etc. So I request Professor Pradeep to please share the screen and enlighten us with the talk.
Yeah. Just check my screen share of
No, no.
It is not shared? Okay. Probably I've shared, no? No. Praveen, share नहीं होता है ना? Sharing happen from here,
yes.
But it is already disabled. तो मैं इसको बंद करूँ फिर join करूँ?
So I think there is some technical problem. Professor Pradeep will join us soon. There should be some technical problem.
Okay, yes, yes. Okay, this one. And also this one. Okay. Yeah, it is not recorded. Yeah? Yes, yes. It is fine. Should I use it or it will record? Okay. Should I start? Okay. Thanks, Dr. Dheeraj, for providing me this opportunity to present my work. And I'm going to present my work on modeling of gaseous radiation and its application. And I'm Pradeep Kumar, and currently associated with IIT Mandi. And this is my laboratory name. And we do basically numerical experiment rather than physical experiment, and we do a lot of experiment and try to mature the concept. Basically, mostly in gaseous radiation is coupled with other modes of heat transfer and fluid flow. Okay, so before going my formal presentation, I would like to give a brief glimpse about the IIT Mandi. This is the location of our IIT Mandi, and it has a very natural boundary. Big mountains, and we are in the recess of the Himalaya, level of the Himalaya. Okay, and we have a quite good environment, and so this is a situation. This is the layout of IIT, and to get a situation, it is a quite clear and sunny sky, and we have a lot of greenery in our campus. So this is a clear day, and when this is a situation when we have rain in our campus. Rain in our campus, it is basically you will feel the clouds on your head, and although we don't get a snowfall, but sometimes it happens. It happens once during my stay at IIT Mandi, probably in 2018 it happened, and this is a situation when we get the snowfall. Okay, so it is a quite beautiful campus, and I would like you to have a visit and come and work with us. And our layout is a little bit different. We faculty and students are residing side by side, so that we have a close coordination to work and produce some output. And this is the situation during the night. Okay, so it is in results. So with that, and a little bit about the temperature. We have a quite moderate temperature, which is conducive to work. Minimum temperature during summer is almost 20 degrees, and maximum is 32. Doesn't go beyond 35. Okay, and winter max 15, and minimum maybe 0 during the night. But once during the sunny day, the sunny winter, we this winter is not that much problematic. But since we don't have a heat storage thing, then once the sun sets, then it becomes chilly. That is a situation a little bit adverse, but otherwise winter is always very pleasant there. Okay, because we are at high altitude, we don't get fog. Okay, so it is clear sunny. Only thing is we don't have a cloud. Then winter is also very. You can say it is very good. Okay, and you have major tourist destination around our campus. Everyone may be knowing the Manali thing. Okay, Plume Manali is hardly 110 kilometer. Simla 130 kilometer, and Dharwad is 140. So you may come, work, and visit, and have outing, good outing as well. So good place to work, and with that, I will invite everyone to come at IIT and have a pleasant stay. And with that, I am going to start with my formal presentation. And before presentation, I should acknowledge some of the students who have contributed whatever I am going to present here. And this work is mostly performed by 3 MSc students, known for Kamal Kumani and Series Karatigar, and 1 PhD student, G. Chadakya. So this is the outline of my presentation. Okay, so I would like to start with the introduction and some equation, modeling of radiation, and this presentation is mostly focused on the radiation because other models, I'm using other models as available in the. Okay. I should speak louder, yeah? Okay. Near to my near to. Okay. Now, how is it? Hello? Okay. Okay. So mostly I'm focusing on spectral, on radiative heat transfer, and I would like to introduce you a new equation that is a spectral radiative transfer equation. And when you are going to take radiation into the consideration, how your energy equation gets modified. and other equations you may be knowing. So radiative heat transfer behavior in engineering problems, and some of the important of radiative heat transfer, and these are most complex and critical applications like thermal load on the rocket base plate, and estimation of the radiative loss in the combustion zone. And with that, I will summarize my presentation. If time permits, then I will also a little bit give you a little bit field of the collimated beam radiation. Okay, so you have come across this situation frequently, and it is very important thing in the north. Okay, this is basically bonfire. We're sitting beside the bonfire and receiving the heat. Okay, so and you're sitting at one place and you are feeling very cozy thing. So looking at this thing, three questions arise. One is how much energy you are receiving, which mode you are receiving, and what is the strength of the source. Yes. So by which mode of energy, which is prominent, which is only mode of energy, that is radiation. Yes. Okay, because you are not facing the fluid flow directly, the convection is ruled out, and conduction because your temperature, look at air temperature around you, and it is almost the same as a thermal, so no conduction, there is no gradient. So only mode of heat receiving is by radiation. Okay, so but how much and what is source strength? Okay, how much basically depends upon view factor, whatever view factor you are making. Okay, and what is the source? The source is basically flame. Okay, these are the hot gases, and they are emitting radiation. Okay, hot gases are basically not hot gases emitting radiation. Radiation is like very few gases, which are having the asymmetric molecule like H2O, CO2, CO. Okay, so radiation goes up to that level of things. Okay, and they emit radiation and they create the source stuff here. Okay, so you may also encounter situation where suddenly flame becomes big, yeah, and you feel more hot. So what does you do? You go by it. Okay, so with theoretical phenomena, you basically invoking here, you basically reducing your view factor, so that you receive heat less. Okay, so you receive heat, and again, new situation, you are very comfortable. Okay, so this is a very good example. Oh, sorry. Whatever. No, okay. Okay. Fine. Again, probably I'm online. Okay, it is not here. It's back? Okay. Okay. Correct? Okay. So now you're very well aware of this phenomena. Yes. Let's go a little bit more complex application. You may have seen this rocket is going up, getting lifted, and a very high temperature pressure plume is coming out, and this is hitting the rocket display. This is display. Okay. So again, the only mode of heat reaching here is radiation because it is upstream of the fluid flow. Okay, and also air is having less conductivity. Also, the temperature almost remain isothermal. So it is only this way. But what is source? Source is this fluid. So we need to find out the source for the radiation. Okay, and ISRO needs a solution for this problem, and they want a solution during the lift-off. Lift-off is very much heating happens. Okay, so during the lift-off, they fired the solid fuel rocket engine. A solid fuel rocket engine basically having the aluminum. So along with other thing, scattering is also a major role here. Is a major role here. Okay, so okay, and what about this? Earlier problems were the heat transfer problem, and you may have seen the heat seeking missiles. okay, which is changing the aeroplane, your fighter jets. Okay, how does it happen? It detects the IR signature from this plume, and IR signature basically is emitted by the CO2, whatever combustion is happening. It is basically chase down this fighter jet, and finally dogfight happens, and depend upon the skill set. Sometimes you dodge this missile, or sometimes missile hit you. Okay, and now with the invent of the smart weapons, you okay, so smart weapons have been invented, and this weapon basically is javelin missile. You may have heard, okay, of this missile during this Ukraine and Russia war. So you may be surprised to see that Ukraine, very tiny country, able to sustain the war with mighty Russia. How it is happening? With smart missiles, smart weapons, smart basically defense system. This is a man-portable air defense system. Okay, air defense system, which basically you can carry on the shoulder and take the aim and fire and target. Okay, it will chase down your adversary, and finally something happen. Okay, so we need to look at all the phenomena happening in these situations. Okay, and here radiation is basically is important role is being played. Okay, so if it is this, then basically there is a prominent myth that radiation is very important in high temperature applications. But this is not always true. It is true. If you look at the natural convection happening around room temperature, and with a small temperature difference, if you try to calculate the radiative heat transfer coefficient analogous to convective heat transfer coefficient, its heat transfer coefficient is still, radiation heat transfer coefficient is still high. But with the increase of the temperature difference, its contribution is almost equal to convective heat transfer coefficient. So whenever you are going to do the ritual convection, you cannot ignore the radiation. If you are going to ignore radiation mode of heat transfer, then basically you are introducing half of the error, and it may lead to a significant blackness. Okay, so if we agree on those things, then what are the way to analyze it? So there are two ways. One is surface to surface radiation model, and there is radiation in a participating medium. Okay, and you can also handle surface to surface radiation model by radiation participating medium. Okay, but you come with some cost. So this is these directly are totally different, and this is but you can also do this. More generalized the radiation in a participating medium. Okay, so let's look at the more general way. Then, if situation arises, then we'll also see the radiation in a radiation by surface model. Okay, so radiation in a participating medium. When a pencil of ray, monochromatic ray. Look at, I'm putting emphasis on the pencil of ray and monochromatic. Monochromatic means single wavelength. On pencil of ray means only one direction. Is going to a medium which is participating. Four phenomena happens. One is absorption, another is emission. Okay, and in scattering, out scattering. Okay, so if consider all phenomena and try to develop equation out of these phenomena, we come across a integral differential equation. Okay, where your variable, dependent variable is spectral radiative transfer equation. Look at this equation we have developed for single direction and single wavelength. Okay, so look at there are multiple directions and there are long range of wavelength. Okay, so this is only for one direction, transfer of radiation energy in one direction and for one wavelength. Okay, and this is a spectral radiative intensity, and IB is a Planck function, and is a refractive index of the medium. Beta is a spectral extinction coefficient, and K lambda is absorption coefficient. Sigma lambda is scattering coefficient, and extension coefficient is sum of these two. And there is another term that is called spectral scattering albedo, which is the ratio. And phi is spectral scattering phase function. It tells how scattering is happening. Okay, and zeta is the direction cosines. And Apart from this, there is a calculator used in this domain, that is optical thickness, is defined by extension coefficient into the characteristic length of the system. Okay, so most of the result I will be explaining with respect to optical thickness. Okay, and if I going to calculate this equation, if I want to solve this equation for every spectral location, that is called line by line method, and this is used for the benchmarking purposes. Okay, so and this equation is solved with the boundary conditions, and there are two kinds of the boundary. One is a diffuse radiation. Basically, it is opaque. If you know, every element emits the radiation, and it is in R direction. So this is the intensity emitted from the boundary, and one is collimated, like your sun ray coming through the window. Okay, so window is also having a temperature. It will also emit the radiation in diffuse direction, along with the sun rays coming through window. So this that is boundary condition is modified by having an additional term for single direction only. For this direction, you are entering the collimated beam. Okay, and if you are going to consider the radiation in your analysis, then your general energy equation, which basically for the conduction and convection, will have additional term. That is that term is basically divergence of radiative flux. Okay, and look at this. This is due to the radiation. Radiation is involved as a sink term. Basically, radiation rule is to reduce energy from your system and distribute somewhere else. Okay, and divergence of radiative flux is calculated by this some emission and some absorption. G lambda is basically irradiation, and irradiation is calculated from the intensity field. So you need to solve the equation. You need to solve the radiation equation, and then you have to calculate the irradiation. Okay, so from this equation has all modes of heat transfer. Okay, and now there is challenge to solve RT. First, look at the behavior of your dependent variable, that is the intensity. Intensity now spectral intensity basically. Okay, it is function of your space along with direction. And who we are doing the CFD may be knowing to resolve the space gradient space variation, you need to discretize the spatial discretization. But along with you also resolve the directions. So you have to also resolve the direction. With there we use the basically spherical coordinate system. So two discretization are involved. Now you have to also resolve the spectral. So third discretization is required. So basically you require three discretization for solving the radiation. Three level of discretization is required. Okay, but before going to take it in any problem, let's look at some behavior of the radiation in any system. Okay, so radiation emitted from any object at 0 Kelvin is not monochromatic. Okay, it contains energy from all spectrum. Okay, when radiation energy interacts with gas, atom or molecule, absorption emission spectrum is generated due to quantized energy level of molecule. And this term is called the line transition. Okay. Other phenomena like broadening, line overlapping, etc. also happens. Okay. And this provides the spectral absorption coefficient, and this concept comes from the quantum mechanics. We don't need to read the quantum mechanics. Okay, but mechanical engineer is also going in that domain, moving towards the domain. Okay, like knowledge is progressing, knowledge getting saturated, we are moving to different level and bringing to our mechanical domain. Okay, but at present we don't need to study because other way also possible to whatever information you need from here that can be available from some databases like CDSC, HITRON, item database also available that provide the line condition. But you cannot. Our objective is to get spectral absorption coefficient. But you need to do some calculation to get the absorption coefficient. But the gas medium hardly contains single gas. Okay, it is mixture of gas, which makes calculation of the absorption coefficient quite cumbersome. So taking consideration of all these things, we need to move forward. Okay, so looking at all those things, our group has started calculating the absorption coefficient, and it is related to transmittivity. So we have taken very simple system, which is a homogeneous isothermal medium. Okay, so and homogeneous isothermal means at one thermodynamic state. Thermodynamic state is defined by temperature, pressure, and mole fraction. So we have taken 100% of CO2 and tried to calculate transmittivity. Transmittivity of the most of the spectrum, it is almost 1, means it is not absorbing. But in some bands, transmittivity is quite low. Okay, it is telling me that gas is, your energy is getting absorbed here, and CO2, and it is not continuous. Okay, so it is basically telling that CO2 absorbs in certain bands and 3 bands. Similarly, H2O is also absorbed in certain bands. It is not a continuous. Okay, so this is at one thermodynamic state. Okay, but life is not that much simple. Okay, and previous graph was quite spectrally average. That's why you're getting smooth. But you look at the narrow band information and look at more resolution. So there are a lot of lines in between those bands. Okay, a lot of lines in those bands. Okay, so these lines basically provide the absorption position, and you have to do calculation of RT on these lines. Okay, and these lines are billion. So we need to solve your RT to solve it at the first from the first method. You have to solve all those lines. Okay. So along with that, we have also calculated the absorption coefficient of air. Although most of the engineering problem absorption coefficient of air is considered as 0 or it is transparent, but absorption happens at very low wave number. Wave number is similar to frequency. It is analogous to frequency, but it is not a frequency error. Only speed of light is not considered. Okay, and with increase of temperature, absorption coefficient keep on decreasing. Okay, so with all this information, let's look at cost involved in calculation of the radiation, because we know there are 3 kinds of displays and there are spectral lines, all those things are there. Okay, so before engaging your resource, you should know how much you are going to pay. Okay, so let's compare it whatever we have experienced, we have idea. Let's solve the Renewables equation on a single cell. Okay, which have 6 phases. So one need to allocate memory at the cell center and center of the phases for 3 velocities and the pressure. Yes. Okay. So single cell, very simplified version. Okay, there are intermediate variables also there, but we are not considering because that is part of the algorithm. They are memory getting located and getting freed. Okay, but this memory will remain permanent. Okay, so with this you need only 28 units of memory. Yes, correct. Okay, but to solve RT or diffuse in all directions, at least you need 100 units of directions. So you need 700 units of memory. I'm talking about it is spectral, only one residual, only at spectral location. Okay, so it's still more than 1 order higher memory requirement to solve the RT. Okay, let's say you want to solve the full spectrum. So there are millions of lines, and you need to solve RT on those millions of lines. So to solve the RT on a single cell, you need at least 700 million units of memory. This is unreasonable number. Okay, current computer technology cannot handle this. Okay, but and also for a cold simulation, it takes deep months time for parallel mode. Okay, it is unimaginable to solve critical problem with radiation in current state of computer technology. People are saying quantum computing can hold this promise, but I am not able to this. I put the word. Okay, this is a jargon I put it here. You may figure it out. Okay, but fact is that in any scenario of heat transfer in closed situation, all modes of heat transfer are present. Okay, and heat transfer needed big consideration. Okay, so look at how situations are complex. Look at if you want to solve only very practical problem. Okay, so this is the situation. You are lifting the rocket. Okay, and your rocket base is getting heated. You should not do over design because they are going for complex mission, and any extra load will hamper your instrumentation and everything, all those things. Okay, so you must have a clear calculation of what heat load are coming here. Okay, so but look at your operating condition. Your combustion chamber is at a 60 bar. Okay, so I'm trying to tell you how many thermodynamic states exist. Till now I have calculated only for one thermodynamic state of the gas. Okay, 60 bar. At outside it is almost 1 bar pressure at low altitude, but at high altitude it is 20 millibar. Okay, temperature they are generating a 3000 Kelvin inside the combustion chamber, and outside is 200 Kelvin. Whatever species, this radiation depend upon what constitution of the species. So what species depend upon fuel. Okay, there are different types of fuel they use it. And look at what phenomena exist for the fluid flow in such a high compressor flow. You have a lot of salts, all those things. Okay, so it's really quite complex. It is not only radiation is complex. Even compressor flow, fluid flow computational is quite complex. Okay, your Mandi, stable point, reflection, obsolves, implicit core, mixing layer, all those things are there. Barrel salts, expansion fans, all those things you need to be done. Not only because these situations would decide your thermodynamic state, and radiation depend on those situations. Okay, look at another black powder rocket fluid. Look at the color of the fluid. It is pink. It is telling it has some different species. Okay. So look, let's revisit some engineering problem. So this I have solved to demonstrate how much whether radiation is important or not important. We have taken four scenarios. One is pure convection, one is surface to surface radiation. But tau equal to 0 means it is basically transparent medium. Only it is radiation emitting from the wall and reaching to the other wall. It is getting unaffected by fluid flow. Okay, and you are engaging some participating medium. This is very less. Tau d optical thickness 0.1, quite optical thin, and tau d is equal to 2.5. Okay, and we are putting this kind of a grid here. Okay, in this to solve this kind of problem. Okay, so look at as soon as we engage the radiation in participating media, your fluid flow is getting cooled quickly. Okay, because you are engaging in a mode of heat transfer and taking heat and throwing out of the wall. Okay, so it is throwing most of the fluid. Okay, because look at the electrolytic situation. Your fluid is entering at 2000 Kelvin and your wall is at 1000 Kelvin. Okay, so your radiation is cooling your fluid very quickly. Along with that, if I increase the absorption coefficient 2.5, look at heat again. Fluid is getting heated because here radiation is optical thin. So radiation playing is long range phenomena. Here before reaching the wall, it is getting heated. So again, fluid is starting getting heated because radiation is switching its role. Okay, but it is very simplified situation is there. Here I didn't use any realistic property model. It is basically transfer mechanism I have already solved. Okay, and using a very superficial property of the radiation. And we are putting this kind of a grid here. So, and it is telling that a cell is isothermal in isothermal and homogeneous. One cell is isothermal, each cell is isothermal and homogeneous, but not two cells because situation is different between two cells. So, radiation from this calculation, it is telling radiation is important phenomena, and assumption of gray radiation, where absorption coefficient is independent of the spectrum, is not appropriate. LBL calculation of non-gray is not feasible. Okay, because thermodynamic states are different in each cell, and LBL calculation involves at least 700 million unit of time unit at time the same proportion for one cell RT solutions. Okay, so but it is important. We need to do something. So hope is not lost. There is still a hope. That is another method, and full spectrum K distribution method. And it is based on some observations. That is a same line transition happens at many spectral locations. It is unnecessary to do the same computational repeatedly. Reordering such line transition into some monotonically increasing function, that is transfer of absorption coefficient in spectral location into some G location, where G is a cumulative K distribution. Okay, so it is just some mathematical calculation we are doing, and we are transferring raw data into some other domain. And advantage of monotonically increasing graph is that one can obtain same accuracy with only few quadrature points. Okay, so when your property is transformed, then your equation should be also transformed. So we are just currently we are using one phenomena at one time. We are just using the absorption emission, and your spectral absorption coefficient is also spectral absorption coefficient is transformed to G domain. Clearly, RT is also transformed, and it has almost a similar kind of equation is almost of similar nature, but it is in different domain. And body condition is also modified, and it is taking one more factor. It is called stretching factor, and this is the ratio of FSKI, the wall temperature, and the reference temperature. Okay, so rest are fine. Okay, so after and how you are going to transform it? You have to divide range of absorption coefficient into small divisions, and taking by this rule only. You cannot take basically a uniform division. And once you transform into monotonically increasing, then selection of the points on those partition points on those graphs is also with some rule. This is the rules. Okay. Once you calculate it, then you can get a total intensity. Our purpose is to get a total intensity. You can integrate it. Okay. Then we start engaging this method. This is a graph of the absorption coefficient, and when we transform it, it becomes a smooth increasing function, monotonically increasing function. This is S2O. This is for CO2. Graph is this is very erratic graph of absorption coefficient happening. Absorption is happening on only certain bands. Okay, now it is very smooth. Okay, and we are taking the range of temperature variation on the at a pressure, and this is graphs are basically mix each other because it is starting from 0 to maximum value, and this for S2 and CO2, but it has a something different nature with respect to pressure. Graphs are basically totally distinguished. Okay, and then we started doing the cases, and this is a development process. We have taken very simplified cavity, which is basically 1000 Kelvin and filled with the CO2. This is isothermal, and its boundary is 0 Kelvin, means there is no emission from the wall, and this is the absorption coefficient. This is basically transform domain, absorption coefficient K distribution, we will call it in the transform domain, and we are taking some points 12, 16, 32, or 64, and look at and we are compared with calculation of RT on this graph. Okay. Finally, we are taking that that's a reduced number of points. Your difference in the result is quite less, but we are getting great advantage. Where calculation we are taking 95 minutes on each and every spectral location, now has been reduced to 0.1 second. Okay, so great disadvantage is little compromise with accuracy. Hardly accuracy within the 1-2%. Okay, so and we start making a case complex, reaching towards a more critical situation. Now wall is also emitting. Okay, and now of the same temperature, now wall is emitting with a different temperature, and your accuracy is keep on coming almost same with the reduced cost. Okay, so again we are taking bifurcated cavity. We are having the two thermodynamic states in the cavity, and we are calculating the fluxes, and we are almost getting the accurate flux. Okay, only less point having the 12 point is having the little bit less accurate, but it is also 1-2%. Okay, so the conclusion of all doing this exercise is that the memory requirement has been reduced from 700 billion to 8,400 billion. So this is realistic. This is not a realistic number. Okay, we have to reach a realistic number. Still, it is more than two order higher than solving the Navier stable equation. Okay, but with that we can start with something, and then further figure out how to further reduce it. Look at radiation is third mode of heat transfer. Okay, any complex problem, only does not contain only radiation or something where radiation is very important. But in any engine solution, you have a fluid flow, heat transfer, and radiation, but it is only 30. Okay? And so we need to further reduce this memory requirement and time as well. We again then we realize that we need to calculate the adjustment coefficient at each and every thermodynamic state. It is not possible. Then we are looking that if for which the thermodynamic state is not available, we do the interpolation. And here thermodynamic state is available for this stream chamber, you can say stream regions, and middle we are interpolating. And looking at the performance of interpolation, and it is coming quite good. Okay, and something isothermal inhomogeneous, something kind of a combination we are checking. With this test, we are basically confident that this method is working properly, and we can engage it. But life doesn't stop here. Problem doesn't stop here basically. Life keep on going. Okay. Okay. Please feel free to ask questions. Okay. You're not getting. Okay. Okay. So look at further. What happens to here? Okay. So basically we are transforming from one domain to another domain. Okay. So we have lost the spectral information. But mixture of gases, we need to calculate the spectral adjustment coefficient for each gases and add it. Okay. But if you are adding into transform domain, it is not straightforward. Okay. So since the engineering problem has a mixture of gases, so we encounter one more problem. That is, adjustment coefficient of mixture of gases is obtained by summing of adjustment coefficient individual gases in spectral location. Okay, that everyone agree. But we cannot take adjustment coefficient by summing of the K distribution in individual gases, basically transform domain. So we need to engage further models. There are many models, but just giving one model, that is a multiplication mixing model. And here you need to get the G K distribution for each gases and get the multiplication from there. You can set the K of mixture. And we are looking at the performance of these mixer models and from LBL and especially addition model and multiplication mixing model and other models, and we are looking at multiplication mixing model is performing better. Okay, for 50% CO2 in H2O. Okay, so after all these calculations, we start taking a simple problem. We start doing some easy problem. It's very simple. It's a very small scale problem, not your big issue problem. We are looking at the problem at a very critical situation. Okay, so this is also heat load case problem. This is a base plate, and we have taken this problem from one paper. Your stagnation pressure is 7.11 bar. Okay, fluid is getting expanded in this 7.11 bar, and drive pressure in the buffer chamber is 1.10 bar. Temperature is 2000 Kelvin, and atmospheric temperature, basically your buffer zone temperature is 288 Kelvin, and we are just taking the CO2. It is basically very theoretical problem. Okay, and look at the dimension. Dimension is quite small. This is throat is already 2 mm, 1.98 mm diameter, and the length is also very small. So this piece clearly falls in optical thin approximation. Where optical thin approximation, basically absorption does not happen. We are only looking at emission. And with this approximation, we can use very Planck mean average coefficient rather than going for the spectral coefficient. Okay, and we have coupled the flow and heat transfer situation model with radiation thing, and we are first getting the fluid flow and heat transfer, and then we couple the radiation. And this is how what happens when fluid is expanding from 7 bar in a buffer zone for 1 atmosphere pressure. Initially there is a transition, and afterwards jet is clearly formed. And you see a lot of socks happening, SOx reflection or viscous layer, shear layer are formed. Once this is formed, then we engage our radiation calculation. Okay, so on a steady state, we are getting speed up to 2.22 Mach number. Okay, and here and also the temperature up to your temperature 2000 Kelvin is coming, and this is the distribution of temperature. This is how temperature is getting distributed. And look at you clearly see the SOx and all those things and there is discontinuity in temperature as well. Okay, and this is the distribution of the CO2. Okay, because your buffer chamber is filled with the N2 gas. Okay, all three things makes a thermodynamic state. Then we start calculating the adjustment coefficient on that, along with the radiation source term. That is our quantity. That is basically heat is removed from the plume. Look at heat is removed. This is heat is removed, and look at in the diverging section, your fluid is getting heated. Okay, and this heat is also getting distributed on the surrounding object. Okay, then we have calculated the flux. We are getting around 4,000 flux because it is very small fluid, and you can relate this to situation. Flame becomes big, you are getting more heat. Okay, so flame becomes big. Okay, diameter of the nozzle becomes of the meter order. Then your flux will be also very high. How much it will be? I don't know. Okay, and temperature we are getting to 334 Kelvin temperature only, but it is a very small scale problem. We only have demonstrated the proof of concept. Okay, so along with that we also did the hydrogen conversion for a small scale. We have taken the non-premix Lambda conversion. Fuel is 50% of S2 and N2, and air is basically oxidizer. And we have used a Kenkin database and transport property we have calculated from the Sudal model. Okay, and Sudal model does not work because S2 being very light molecule, it diffuses very fast. So you need some advanced model for the diffusivity. That is a multi-component diffusion model, but we couldn't do that. We're looking to do that. Okay, so this is your loss of the radiation in the flame, and compared with your Plume, which is very primitive model, with your more accurate model, that is FSK, and look at that your loss FSK is giving more loss in the plume. More loss in the plume means temperature will getting reduced. Okay, so this is how peak temperature is getting reduced. This is by experimental, and this is the Plume, and A for the FSK. FSK for the reduce the 100 to 200 degree from the peak temperature, and also we are getting the heat on the cylindrical surface, and heat is also different on the cylindrical surface by these two property model of the radiation. Okay, so with that, I'm going to summarize of this part of the presentation, and through this presentation, probably I'm successful in establishing that radiation is an important mode of heat transfer. Okay, but careful judgment is required to include radiation transfer in the analysis as complexity increases. Radiation by Gray approximation is hardly realistic. Okay. FSK method reduces the requirement of computer resource for the Gray radiation calculation significantly. On-the-fly calculation of FSK is not advisable because developing a lookup table for adjustment coefficient, database for adjustment coefficient is way forward to include the non-Gray method of the radiation where high degree of inhomogeneity and non-isothermal exists in the system. With the current approach, the spectral information is lost. However, it can be reconstructed for the study of higher signature. Significant work is required to make the use of radiation heat transfer. Thank you for attention. Okay, so if you have further time, then I can present another work. Dheeraj, what do you say? It's a time plus question on this part of presentation. Okay, if you have any question, I will happy to answer. Any question from online audience?
This question.
I don't know. Oh. No, I didn't mute anything. Okay.
Okay, so yeah, the question is from Professor Remankar. He says, please throw light on radio frequency ablation used in medical therapy. Radio frequency ablation used in medical therapy.
Okay. I would say that I haven't worked in that direction. Okay, because this is a tissues. We need to check the properties for those. And till now I have only concentrated on the radiation property of the gases. Okay, so tissues, skin, and all those things, I need to check their properties. Although these equations are very well applicable, but we need to be careful about the properties, whether properties are available or not available.
Professor Remankar, is that audible? Is
Sir.
it okay?
Yeah, sir. Yes, sir. I had one more question. You can please take up, sir.
Hello?
Yeah, sir. Yeah, I got the answer.
Second question is from Professor Remankar again. In comparison to other modes of heat transfer, radiation mode is less understood. So,
Radiation mode is?
Less understood.
Yes.
So, you can comment on that.
Yeah, main reason for this, the tool is not available. Until it is very simplified tool is available and more we need to put more resource in it, then we can make it more easy and easy to use. Until less more people will be working on this field is not going to get simplified. Earlier, CFD was also very complex. A lot of people kept on working and making this very simplified, and now commercial companies have also come up make the tool very easy. Now everyone is using the CFD. Similarly, in radiation, apart from this thing, radiation has another level of complexity, that is property. Okay, although every transfer mechanism depends upon the transfer mechanism and property, but other properties of fluids and solids and almost continuous and almost constant. And less variation with, you can say, sometimes we take the variation in temperature, but this we can get a polynomial and we do it. But complexity here comes that it's variation with space along with the spectrum. So we have to look at in this aspect that it is complex, tool is not available, and two levels of complexity. If you're able to address and make it simplified, and more people will keep on working, then basically we can come with some way that where it is important, where it is not important.
Thank you,
we are
sir.
looking to develop the tools. When tool is available, then basically.
Yes. Thank you, sir.
We'll start working on it.
I have a question regarding the discretization that you showed, X, Y, Z, theta, and phi. So XYZ should be uniform, or it can be non-uniform discretization as well?
It can be anything. Yeah, it could be non-uniform. Yeah, but since the equation is quite linear, if you look at equation is quite linear. Then basically, and it is taking too much resource. Then basically, we need to work. If you really want to deal with radiation, you need to reduce computational resource as much as possible. So one idea is that you can work whatever grid is available. Otherwise, if you want to make it faster, then basically you have a dual grids kind of system. You solve this RT on very coarseness and transfer all the quantity to a fine grid where you are solving the fluid flow. Okay, so agglomeration of the grid, this kind of idea is coming up. We need to put more and more work into it because this is, as I presented, it is very costly domain. Okay, so yeah, you have to make it simplified and make it fast. You cannot run it and keep sitting idle. Okay, otherwise you will lose the interest. So make it to make it fast, and mostly effort is going on to make it fast. So we need to work on the dual grid system, and it is basically, look at question. It is basically almost linear. So you need not to have that is defined grid for RT.
When you solve the problem for flame, the combustion, the flame, there you, whenever there is a combustion happening, we know that there are temperatures in the flame also, right? There is higher temperature at the, whenever there is actual reaction or release rate is, heat release rate is there. And maybe you have diffuse flame, because it's a diffuse flame, you have this lower temperature in the inside of the flame compared to where the reaction is happening. So that means the radiation, what you call this contribution, is more from that region where you have higher temperature. No?
Radiation depend two things. One is absorption coefficient, depend upon the participating species, and temperature. Okay, with increase of temperature, absorption coefficient keep on decreasing, and emission is basically A times temperature, means emission. Okay, so A is, with temperature A is decreasing, but A is also depend upon the participating species. So a clear answer does not exist. Okay, but whatever study we have performed, we are seeing that yeah, within the core, your radiation is heating the fuel line, yeah, and from the flame it is reducing the heat. So it is playing source and sink both role. It is not only one role. Some it is basically some, it takes the heat from one location and put the heat in another location. So it redistributed the heat. So temperature is getting redistributed with the radiation. Yep.
So, you showed an image where there was a rocket and the nozzle and the flames. So you said that base plate is there. So you were trying to say something like radiation is reaching the base plate from outside, or you included inside the nozzle.
Okay. I am saying this is base plate. Yes. I am saying the radiation is emitting from here and reaching to base plate. So whatever heat is coming onto it, what is source of this? Okay, source is this. Okay, that's why the first graph, in the first picture I told you that three questions come. What is the strength of the source? Until you know the strength of source, you cannot say how much heat is reaching here. And which mode? Only because it is upstream, only radiation is possible.
So to study this, we can slice this, imaginary slices, like we do study for the fluid in laminars. Every disk will be having, we can consider like vertex flow we discussed in the laminars.
No, not like that. Not like that. Look at this this thing. From that we did it. Okay. Look at this is heat is removed. Okay. This is your jet. This is jet. Okay. Jet has a lot of thermodynamic states. Okay. And thermodynamic state is basically decided by what is basically pressure. Pressure is proportional to this magnitude as well. Okay, it is in the same proportional. Inversely proportional, there is pretty right, but you can say it is related to pressure, temperature, and species concentration. Okay, so this is decided by what is happening here. Okay, because CO2 is participating, and other domain is filled with the N2. N2 does not participate. Okay, let's look at other thing apart from this jet. Other part you don't have any source. Look at zero, almost zero. Okay, so here only it is synced up. This is energy is getting reduced from the plume, and it is distributed everywhere here. But our interest is how much is getting here. So that we have calculated. Okay. Yeah. It is nothing. It is mathematical basically duty. Okay. It is just. I'm not going to tell you the equation, otherwise you will not be interested. This is the data in the adjustment coefficient. Yes. Okay. This is actual at one thermodynamic state only. Okay. You just take this data and transform it. Okay. All data is transformed into this domain, and you get a monotonically increasing function. And you know, integration over monotonically increasing function is very smooth and very accurate. Same thing. It is just mathematical beauty. Nothing. Although FSK is very complex. Okay. If you read, basically, it is all borrowed from the atmospheric science. Atmospheric science, you know, your whole climate is governed by three phenomena, mostly three phenomena: fluid flow, heat transfer, and radiation. Okay. That's why this field is very close to nature. Okay. So if you allow, I will show you in the simulation as well. Okay. So radiation, and radiation is very well developed, and you know this CO2, H2O, lot of talk is happening that if that much CO2 emitted, then average temperature will increase 3-4 Kelvin, and then ocean that much rise, ocean that much country would submerge, and all those things. Where all those is coming? It is all coming to simulation only. There is very good source code is available. Okay, so it is borrowed from here, and now it is popularized mostly by Professor models, FSK method. Although two methods are there, both are common. One is FSK, full spectrum gate distribution, and there is SLW, spectral line WSC basically, spectral line weighted sum of gray gas method. Okay, and both are same. Only both are talking about you have to real them. So that whole effort is going on to reduce the cost as much as possible. People know how to solve it. Not able to solve because it's taking too much time. And we need to reduce the cost, reduce the time as much as possible. Otherwise, people will lose the interest, people lose the concentration, and will not learn. Okay. So whole effort is going on to reduce. Okay. So I will not go for all the questions. Okay. So once you know the idea, then you can figure out what is happening. Okay, you take the basically division, small division, and keep putting this volume D division to here, and you construct the graph. Okay. Any more questions? Okay, it is nothing. Okay, but look at it. This is how you thermodynamic state. So look at Plume case. How many thermodynamic state exist? There are numerous. How to do that? As much as cell you put, that much thermodynamic state is available. Okay, that's why I told you that you need not to take the same rate as in a fluid flow, because fluid flow you resolve many things, but radiation you have to take a two-grid system, other grid, where is little pores, and you solve RT on those two grid and transform the information of radiation on those grid to this grid, and you will get quite good. Okay, so you have that quickly.
I think there are no online. There's only two questions online, so I think I can thank you now for the online audience.
Okay.
So thank you for this talk on radiation, and we have learned that this is where basically a lot of contributions needs to be made,
Yes.
and it is where you have to discretize in both x, y, z, and as well as the other theta and phi direction. Spectral scheme. So,
Yes.
so thank you for this talk. I thank the online audience for their presence.
Thank you, sir.
If you have any further questions, you may contact the speaker directly at IIT Mandi, his website. So thank you again. Thank you for joining. So I'll close the online.
Okay.
Huh?